third lecture. This one's short and sweet. I packed a lot of information into this lecture in a short amount of time and a short amount of space, pretty much covering just the basics of population genetics. Population genetics also is called Hardy-Weinberg equilibrium. Like those two go hand in hand. And Hardy-Weinberg equilibrium is a portion of population genetics that we are going to look at today. Population genetics can get incredibly mathematically complicated in a very short amount of time. So I'm going to try to keep it as basic as I can. So ultimately, population genetics is about how we can predict genotypes from allele frequencies. If we're able to look at allele frequencies, we can get an idea of what sort of genotypes we should expect to see in future populations. And if those allele frequencies don't line up to what we're seeing in the genotypes, then it's typically an indicator that there's some sort of selective pressure happening, like natural selection's happening on that population. But I digress. Let's move forward. Where are we at? Okay. So because evolution is the change in allele frequencies over generations, it's important to understand how and why populations evolve. That we have to first be able to calculate allele frequencies. And so this first part of this lecture is just how do we calculate allele frequencies from looking at phenotypes. So allele frequencies are just like the proportional number of certain types of alleles in a population. For example, let's say like a population has two alleles for one gene, big A and little a. The proportion of the big A alleles is calculated by counting the total number of those A alleles in the population, but then dividing it by the total number of alleles. So if there's only two alleles, then we calculate the frequency of little a by the same way. So you would say, okay, let's take a look at this. So in this population, let's use this as an example. Big A codes for a big head, little a codes for a small head. We used this in our last lecture. And this is expressed with incomplete dominance. And so what that means is that we see three phenotypes for each of the genotypes in our population. We're going to count the alleles of each type, each of the big A type and each of the little a type. So first we have to genotype everybody in the population. So notice how we did this. Individuals with a big head are going to have two big A alleles. Individuals with a medium head will have one big A allele. And then individuals with small heads will have 0 big A alleles. So all we do is just count the alleles. This individual has 2 of the big A's. This individual has 2, so that's 4. This individual has 2, so that's 6. This individual has 2, so that's 8. And this individual has 1, that's 9. This individual has 1, that's 10. So I have 10 of the big A alleles. Then I count all the little A alleles. And I know that the little head person has 2. Heterozygotes have 1, so that's 2 plus 1 is 3 plus 1 is 4. So I have 4 little a's for a total of 14. So if I'm calculating the allele frequency of A, of big A, I simply take 10, which is the frequency that A appears in the population, and divide it by the total number of alleles, which is 14. And that should, sorry, something just got in my way there. And divide that by the total number of alleles in the population, which is 14. I do the exact opposite for the little a. So I just say the number of little a alleles, which is 4, divided by the total, which is 14. And that should give me the frequencies. And the frequencies will typically be a decimal. It'll be like 0.71. I'm rounding these numbers, by the way, 0.71 and 0.29. All right. Now for the Hardy-Weinberg aspect of this equation, we say that for two alleles in a population, let's say they're big A and little a, the allele frequencies must add up to 1. If it was 3 alleles in a population, the 3 allele frequencies would add up to 1. If there was 4, they'd have to add up to 1. All the allele frequencies have to add up to 1, and that's a mathematical certainty because of how we calculate each allele's frequency. Because the frequencies of each allele are the proportion of that allele relative to the total, well, each proportion should add up to the total, which is 1 or 100%. I mean, you can see that right. You can see that right here with these two. The 0.71 plus 0.29 adds up to 1. So the frequency of A plus the big A plus the frequency of little a will always equal 1 if there's only the two alleles. Okay. So Hardy-Weinberg actually uses a different designator. So he uses a generic form of labeling alleles as P and Q. P is essentially the same thing as big A, and Q is essentially the same thing as little a. So we can either write it as P plus Q equals 1, or if we're talking about a specific allele, big A plus little a equals 1. And those are the frequencies of each one of those. All right. So according to Hardy-Weinberg, P plus Q has to equal 1. So once we determine the allele frequencies, once we figured those out, we can use those allele frequencies to predict the frequency of each genotype in the population. And this is simply done by asking, what's the probability that I pull out two alleles of a certain type from the population, or from the gene pool? So think about it like this. If the frequency of P is 0.5, meaning that half of the alleles that are floating around out there are of the P variety, and the other half are Q. If I want to figure out what's the probability that I make a PP genotype, or P squared, or two big A's, what's the probability I pull those out and make that genotype? I take the frequency that that allele is in the population, in this case it's 0.5, and I simply square it. I just say, okay, what's the probability I pull out one and the other? Well, that probability is the frequency of the one times the frequency of the other allele. And if it's the same allele, it's the same frequency, but squared. So another way that you can do this is you can do it using the FOIL method. So you could say, okay, well, if I want to figure out genotypic frequencies, I'll simply square the frequencies of both alleles, right? So I'll square both sides of this equation, which you can do in math, right? This is like math 0.125 or something. So you're doing the FOIL method, you square both sides, and then you can expand that that equation out. And what you'll notice is that the genotypic frequencies also have to add up to 1, because the proportion of one genotype plus the proportion of another genotype plus the proportion of the last genotype encompasses all genotypes in a population, so they all have to add up to 1. So what does this look like? It looks like this: P squared plus 2PQ plus Q squared equals 1. Now you might say, well, where does the 2PQ come from? Because that part's a little bit confusing, right? We understand where the P squared comes from. We understand where the Q squared comes from. But the 2PQ is a little bit confusing. Why is it 2PQ and not just PQ? Here's where it happens. So you can think about allele frequencies, especially if there's only two, being like flipping a coin, right? So the heads on a coin, you have a 50% chance every time you flip the coin of getting heads. You have a 50% chance every time you flip the coin of getting tails. But what's the probability that you get heads and tails with two coin flips? There's two ways to get heads and tails in any order from a coin flip. You could flip a coin and get heads first. You could flip a coin and then get tails. Or you could flip a coin and get tails first, flip a coin and then get heads first. So there's two different ways to make the heterozygotes from a population. You could get it by pulling the dominant allele out first and then the recessive, or the probability of pulling a recessive allele out and then the dominant. So there's two ways, two events that will make that frequency happen, or make that combination happen. That's why it's 2 times the two frequencies. And we can also write this equation as if it was just an allele that we're familiar with, like big A plus 2 big A plus 2 little a little a. And that's the same equation as P squared plus 2PQ plus Q squared. So the question is, how do we get these formulas? Okay, so there's a couple of different ways we could do it. We could do it by the FOIL method, which you guys are all familiar with, hopefully. Or we could put it into a Punnett square. And this is actually another way of showing how we could calculate allele frequency, or how we can calculate genotype frequencies from using the existing allele frequencies in a population. So to figure it out, you put P and Q, the frequencies of P up here and Q over here, and then also put the same frequencies of P over here and the same frequencies of Q over there. And then in the middle, that's where you multiply. So the probability that you get a homozygous dominant genotype is just the probability of pulling out a P allele from that population. And the probability of pulling that P allele out of that population is the frequency at which that P appears in a population. Okay, so that's P squared. That's how we get P squared. Then you get PQ is the P times Q. You get another PQ, which is Q times P. That's how you get the 2PQ. And then you get Q squared for the final one. That's how you figure out the homozygous recessives. You can also do it exactly the same way, but with A, big A and little a. You say, what's the frequency of big A? Put that here. What's the frequency of little a? Put that here. Put them on both on this side. And then that gives you the matrix of, okay, what's the probability I have a homozygous dominant genotype? What's the probability that I have a heterozygous genotype? 2 big A times little a. And then what's the probability I have a homozygous recessive genotype? And that's how we add up. That's how we calculate those ones. Okay, now I'm going to work through just like a real practice problem with you guys using some examples from our, just using some made up examples. So imagine there's a gene with two alleles, big A and little a, and we know the frequency of the big A allele in the population is 0.45. So that means if I put all of the alleles in a big giant pool, I have a 45% chance of pulling out a big A allele. What is the frequency of the little a allele? So I'm going to pause, you pause it, and then you take a second. What would be the frequency of the little a if the frequency of the big A is 0.45? Well, we know that big A is 0.45, and we know big A plus little a should equal 1.0. So 0.45 plus what is equal to 1.0? So subtract 0.45 from both sides, and you end up with little a, or the frequency of the little a allele, is 0.55. And you can check that. You say, okay, does 0.55 plus 0.45 add up to 1? And the answer is yes. So now the question is, what kind of genotypes and phenotypes can we expect to see in this population that has a gene pool that looks like this? So how do we calculate genotypic frequency? Well, we know the frequencies of the two alleles, so we can put them into our Punnett squares, and we can figure out what the ratio of genotypes I'm going to expect to see with those frequencies. So here's my gene pool, and this gene pool literally represents what I just pulled out here. The frequency of the big A allele in this gene pool is 0.55. The frequency of the little a is 0.45. Haha, that's funny. I switched them. It doesn't matter anyway. So switch these two around, and that's what they are in this example. So pretend this is a new example. So big A is 0.55, little a is 0.45. Okay. Now, what ratio of genotypes can I expect to see with my allele frequencies in this arrangement? Well, here's my gene pool where the big A appears at 0.55 and the little a appears at 0.45. So that means if I reach into this gene pool, I have a 55% chance of pulling out a big A. If I reach into this gene pool at random, I have a 45% chance of pulling out a little a. So what's the probability that I pull out two big A's? Or what's the probability I pull out a heterozygous genotype or a homozygous recessive? Well, I'm going to place my allele frequencies in the Punnett square, in the matrix, around the edges here. And then I can use that to help me predict what the probability will be of pulling two big A's out at the same time, back to back, or a big A and followed by a little a, or a little a followed by a big A. I add those two frequencies together, and then or a little a followed by a little a. And so this is the probability I pull out a big A, and then another big A. I multiply 0.55 times 0.55, I get 0.30. This is the probability I pull out a big A and a little a. It's 0.25. It's the same for the other side over here. Right. One is the probability I pull an A out, a big A out, and then a little a. The other one's the probability I pull a little a out, then a big A. But they basically both make a heterozygous, so I add those two frequencies together. And then the probability I get a homozygous recessive is the probability I pull two little A's out back to back. So what are my predicted genotypic frequencies? Well, my big A frequency should be 0.3. My big A, little a, I have to add these two together, so I get 0.5. And then my little a, I get 0.2. Now, the way I can check my math is I say, okay, do my genotypic frequencies add up to 1? Does the proportion of homozygous dominant plus the proportion of heterozygotes plus the proportion of homozygous recessives all add up to 1? And they should, because that should encompass all individuals in that population. All right, here's some more practice for us. So look out here at this population. So what I'm going to give you a chance to do is pause the simulation. We already know that there's incomplete dominance here, so you guys can figure out the genotypes of these. You can then figure out the number of each allele that's in the population. You can figure out the allele frequencies, put the allele frequencies into your matrix, figure out what the proportion of expected genotypes will be, and then put them here in these blanks. So go ahead and take the chance, just pause it and work through that real quick. Okay, so what we're going to do is genotype this population first. Genotype, then count. So we have individual big A, big A. We know the small heads are little a, little a. The normal heads are big A, little a. And so we genotype them all, and then we count the number of alleles. So what we're going to do is say, okay, how many big A alleles are there? Okay, well, there's 2, 4, 6, 8, 9, 10, 11. There's 11 big A's. How many little A's are there? 2, 4, 6, 7, 8, 9. There's 9 little A's. So for a total of 20 alleles. Now let's calculate the frequencies. So the frequency of big A should be 11 divided by 20. Little a is 9 divided by 20, which makes 0.55 and 0.45. Add those together, they should add up to 1. How do we calculate the genotypic frequencies? Well, we put our allele frequencies in a matrix. We finish the matrix, and then we put those allele frequencies, or those genotypic frequencies, over here. So the big A is 0.3. The big A, little a, or heterozygotes, are 0.5. And then the little a are going to be 0.2. And to check our work, do these add up to 1? The answer is yes. Okay, some more practice. Okay, if we have these genotypes, right? Let's say that these are the expected proportion of genotypes that I expect to see in the next generation. So what if the next generation was 10 people? How many people would have each genotype? Well, all you have to do is multiply the proportion by the total number. So if there was 10 offspring and 30% of them are of the homozygous dominant genotype, well, that should be 3. The heterozygotes, if they're appearing at 50% in the population, you would expect half of the 10 to be heterozygote, so that would be 5. And then for the homozygous recessive, same thing. Multiply that by 10, you get 2. And so that's how many of each genotype we would expect to see. So we would expect to see 3 big-headed people, 5 normal-headed people, and 2 small-headed people in the next generation. So let's start over with that, right? So we got the 3 big-headed, 5 normal-headed, 2 small-headed. What are the allele frequencies for this population? Do it. Pause it. Start over. Do it. All right, welcome back. Let's first genotype. So I didn't actually fill that out for you guys. I did that so you guys could do it. But I can do it with you real quick. So we've got 3 big-headed people. So that's for the big A, that's 2, 4, 6, 7, 8, 9, 10, 11 of the big A. And then for the little a, I have 2, 4, 5, 6, 7, 8, 9. So 11 and 9 for a total of 20. Whoops. For a total of 20. So 11 divided by 20 is 0.55. And then, wait, 9 divided by 20 is 0.45. Wait, why didn't the allele frequencies change? What do you think happened there? Why didn't the allele frequencies change? Well, I can tell you why they didn't change. It's because there was no selection, there was no mutation, there was no migration, there was no, nobody was having more kids than just 1 per person. So those things were keeping the allele frequencies the same from generation to generation. And I'm going to touch on those after we address this one last thing, which is, what if you cannot count allele frequencies directly? So what that means is, like, let's say there's a gene where there's 2 alleles, where one is dominant, the other is recessive. Well, how can you tell who's heterozygous and who's homozygous dominant? I mean, you're not going to go do a test cross with all the heterozygous, homozygous dominant individuals. You're not going to go do test crosses with the dominant phenotype, right? That would take way too long. So how could you estimate the allele frequencies if your heterozygotes are expressing the same phenotype as the homozygous dominant people? So let's take a look at that. So what does that even look like? Well, with our situation here, that means that people that are heterozygous would have a big head, just like the homozygous dominant people, and that the only people who we really know what their genotype is going to be the small-headed people. So let's look out here and say, okay, well, look at this population. I've got 1, 2, 3, 4, 5, 6. I've got 6 people that are a mystery. They could be homozygous dominant or they could be heterozygous. They're a mystery. I have no idea. But then I have these 2 individuals that I do know they're little a. I know their genotypes. So the problem is, I don't know what these guys' genotypes are, but I do know what these guys are. And so what I can do is I can come to my formula here and I can say, okay, my distribution of genotypes in this population is p squared plus 2pq plus q squared equals 1. Well, the problem is that the p squared, which is the big A, little a, the p squared, which is the big A, plus the 2PQ, which is the big A, little a, those are 6 out of the 8 individuals in my population. But I can't isolate that and figure out, and I can't solve it for one of the variables. I can't solve that for Q, and I can't solve it for P. But what I can do is I can say, oh, look, my Q squares, which are these guys, are actually 2 out of the 8 people. So what I can say is I say, okay, I can't solve for P and Q here, but if I know that 2 out of my 8 individuals are homozygous recessive, I can solve for Q. Look, I can take Q squared is equal to 2 over 8, or 1/4, or 0.25. And if I take the square root of both sides, that will give me Q, right? I can solve for Q. So Q is equal to, oh, I'm sorry, my thing is getting blocked here. So my Q allele, or my homozygous, or my recessive allele, appears at a frequency of, it's not 0.25, I messed that up. It's 0.5. Let me fix that real quick. So if you look, the square root of 1/4, or the square root of 0.25, is 0.5. So the frequency of my little a allele in this population is 0.5. Well, then what does my allele frequency have to be for the other one? Well, if little a is 0.5 and big A would have to be 0.5 as well. So I'm glad I caught that. I just didn't go through with the square rooting part. Oops. So let's back that up. Okay. So we know that we estimate that the frequency of Q was 0.5. And we did that by taking the square root of Q squared equals 2 over 8. So 2 out of the 8 people had the genotype Q squared. So I solved for Q. I got 0.5. I know P plus Q is equal to 1. So Q has to be 0.5, then P has to be 0.5. So if little a is 0.5, then big A has to be 0.5. And that's my estimated allele frequencies. I don't know if they're accurate or not, but it's the best I can do from my data. Okay, moving on. Hardy-Weinberg equilibrium. This is what I wanted to come back. All right, so Hardy-Weinberg equilibrium is the null hypothesis. Null hypothesis is this, all right? Let's say I have a blood pressure medication and I want to test it out on a group of people. So I take a bunch of people that have pre-hypertension or hypertension, and I'm like, hey, let's take this group, let's randomly split them into 2 equal groups. I'm going to give one group my medication, the other group I'm going to give a placebo to. My hypothesis is that my medication I just spent $1 billion researching is going to work. My null hypothesis is that it's not going to work. So the null hypothesis is that nothing's going on in this, that the changes, that the difference in blood pressure, the change in blood pressure from my experimental group and my placebo group, the changes I see are just due to random chance. It's not due to anything happening. That's my null. I want to prove my null wrong. I mean, you can't prove anything in science, but you can infer it. I want to infer that my null hypothesis is wrong. So consider that moving into Hardy-Weinberg equilibrium. The null hypothesis is that nothing's going on in this population. So what does that all mean? So Hardy-Weinberg equilibrium is achieved when allele frequencies do not change over generational time. So what does that mean in contrast to evolution? Well, Hardy-Weinberg is this statement that if Hardy-Weinberg equilibrium is happening and allele frequencies are not changing, then a population is not evolving. If a population's allele frequencies are changing, it's evolving. If they're not changing, it's in Hardy-Weinberg equilibrium, which is the null hypothesis. Stand by. All right, where were we? Okay, so Hardy-Weinberg equilibrium is achieved when the allele frequencies don't change over time. So that equilibrium basically equals no evolution. Well, we know that populations are always evolving, so Hardy-Weinberg is the null hypothesis. What that means for us. So in order for populations to be at Hardy-Weinberg equilibrium, that means they have to have the following things happening, okay? No natural selection. So the change in allele frequencies due to their adaptive value is natural selection. So let's say allele frequencies are changing and it's due to their adaptive value, that's natural selection. So in order for a population not to be evolving, to be at Hardy-Weinberg equilibrium, there can be no selection happening. Okay, the next one is there cannot be migration. People cannot be coming into a population or leaving a population. That's going to change the allele frequencies, and that's going to remove the equilibrium, right? That steadiness of allele frequencies over generations. That means there can be no mutation. That means a big A cannot randomly mutate into a little a allele. That alters allele frequencies. Mating has to be completely random. That means there can be no sexual selection, because sexual selection means that there is an allele that codes for a trait form that some female or male finds more attractive and will make more offspring with that trait form, which will propagate that allele in the population more than other alleles, which will change the allele frequencies. So mating has to be completely random for Hardy-Weinberg to be in equilibrium. And so that, yeah, so we, like we said, non-random mating allows for certain alleles to have a higher reproductive value and increase in frequency. And then finally, in order for a Hardy-Weinberg equilibrium to actually work, you have to have an infinitely large population or gene pool. And here's why. Remember when we went back to that thing where we had a gene pool and I said, okay, what's the probability I pull out a big P allele? What's the probability I pull out another big P allele? Well, if there's only 10 alleles in that population, like in that gene pool, if there's only 10 alleles and 5 of them are the big P type and 5 of them are the little p, as soon as I pull out one big P, well, guess what? Now there's only 4 out of the 10 that are a big P. So that changes the probability that I pull out another big P. But if the gene pool is infinitely large and I pull out a big P, that doesn't change the allele frequencies for when I pull out the next big P. And I know some of you math nerds out there were probably like, wait a second. But okay, now I've explained why. Okay, so infinite gene pool population size. So the larger the population, the less random events are going to fluctuate the allele frequencies over generational time. So let's think about this. Is there ever a population in this world that has all of these things happening? No selection, no migration, no mutation, random mating, and an infinite population? No, hell no. So Hardy-Weinberg equilibrium is not realistic. So the question is, why do we even bother with it? Okay, and here's why. When a population is in Hardy-Weinberg equilibrium, the allele frequencies stay the same. So what that means is that if we see a change in allele frequency, it has to be assumed that one of those previous prerequisites are being violated. What does that mean? Well, then we can actually go and investigate and see which one of those prerequisites is being violated that's changing the allele frequencies. So it will tell us it will give us some vital information. It'll give us a reason why evolution is happening on that population. Is it because people are migrating into that population? Is it because a certain allele has more adaptive value than another allele? Is it because there's non-random mating going on or sexual selection? Is it because the gene pool is really small and we've got some case of genetic drift happening? So it gives researchers something to go on, something to base their ideas on. Just like my analogy for the blood pressure medication, if we're looking at the two groups, right, and the one that received the treatment, the one that received my blood pressure medication, not the placebo, the one that received the medication improves their blood pressure scores like significantly more than the other one, then we can say, aha, look, the probability that this difference in the change of the probability that the difference I see between the two groups, the difference where one group, the one that I gave my medication to, all their average blood pressure dropped 20 points, and the other one only dropped like 0.5 of a point. The chance that that was due to chance and just a random sampling problem is like really, really low. And so the probability that the null hypothesis is true is really, really low. It's the same thing with Hardy-Weinberg. If I see allele frequencies changing over time, the probability that that's just, you know, randomness is very low. It's probably due to a small population size, non-random mating, migration, mutation, or selection. And so that's why we bother with it. And so that's it going into the next lecture. And the next lecture is really where we just flesh out all of these principles that we've talked about for the last 3.5 modules. This is where we say, okay, we understand the relationship between genotype and phenotype. We understand the relationship between allele frequencies and phenotypic frequencies or genotypic frequencies in a population, we start to understand and see that when allele frequencies shift and change, that means a population is actually evolving. That means their trait forms and the proportion of those trait forms in a population is shifting and changing. And so we really get to dive into the mechanism underneath why that sort of stuff happens when we talk about evolution in the next lecture video. And then it all comes to a head in the final one with the history of life on this planet. So I will see you guys for the next one.